and final exam will be the week after next week. OK， 下个礼拜。你知道我前几天看到，因为我常跟大家讲说，哎，下礼拜怎样，就 next week 怎样。结果我就在我的手机还是什么的那个推播上就说英文教学的那种广告，他就说你知道下周不能讲 下周不能讲 next week 吗？所以我讲 the week after the next week。好，所以这真的是他一定有在偷听我讲话，我很确定。OK，so let's continue our lecture. I believe I will finish. I believe I will finish on next Tuesday. So yeah, Tuesday. Because I only have several pages left. Right. So yesterday we talked about some example, right? The example will be was the Morse law. Morse circle. The Morse circles, we firstly define the origin, okay, by using this sigma average and R, and we can get the circles. And then we are going to define the plane A in the circle space, point A, okay, by using their component of the stress. The stress can directly used as their coordinate of that point. Okay, so you can specify the point and then set that as the theta equal to 0 degree. And then you can using this as the starting point and get every angles as the inclined section to this 0 to 2 pi, and you can get everything. Okay, and remember that the tau x1 y1 has downward positive. Okay, and and the theta in the real world is doubled in circle world, and in the circle world, the P1 is the right hand side, the point in the right hand side, and the point in the left hand side will be your minimum of the sigma 2, and also your top and bottom points will be your maxima tau, maxima shear stress occurred, and then you can use the geometric problem to solve all the stress point, all the stress component in all the direction. Okay, so that's it. And then we talk about stress due to plane stress, strain due to plane stress. Okay, so the most important thing in this is that even if we only have the component align on xy plane, okay, sigma x, tau xy, y. So there's no z direction in this for stress. However, the normal strain in z direction still has non-zero value because of the Poisson ratio. Okay, the Poisson ratio due to sigma x and sigma y. So you see epsilon z are always kind of shrink in plane stress problem, but this is non-zero. Okay, so be careful about this. And your epsilon x, epsilon y can be written down in two contributions. The first one is sigma x divided by E. The other is the lateral Poisson ratio effect. So minus nu sigma y divided by E will be epsilon x, the second contribution for the epsilon x. And also shear strength and normal strength can be regarded as independent cases. They won't affect each other. Of course, in the real world, they will affect to each other a little bit, but in this case, in the mechanics of material discourse, because they are all small value. So like we regard it as they are independent. Okay, and this is some special case we introduced in chapter 2 and 3. And then we talk about volume change. The volume change is that we set the original volume ABC and the volume after deformation. So after we time them not together and then we can multiply them together, we assume the strand are small. So neglecting the higher order term. So you can get V1 approximately ABC 1 plus epsilon x, epsilon y, epsilon z. So you see that this one is kind of original, right? The epsilon x plus epsilon y, epsilon z, the summation of them can be the kind of ratio. You see, this is 1. This is the increment ratio. Okay, so the change per unit volume is epsilon x, epsilon y, epsilon z. And this is really interesting. I believe I talk about in advanced course, right? We at the advanced course, we have the sigma in matrix form. Remember that? We said sigma 1, 1, sigma 1, 2, something like that, right? Epsilon also has exactly the same thing. So actually in the advanced course, epsilon can also regard it as different direction. So epsilon can be written as epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3. And of course, epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3, you know that they are for shear strength. Okay, shear strength. So although in mechanics of material, this course, we call this gamma, right? But they actually epsilon 1, 2, epsilon 1, 3, epsilon 2, 3. Okay, so the upper triangle is shear strength, and the diagonal term is the normal strength. So you see 1, 1, 2, 2, 3, 3. So in your future, in the future, when you talk about the epsilon in the more general term, just looks like that. And when you see a material subject to a load and they have the material has the strength state describing in this material in this strand matrix, and then we immediately know that epsilon 1, 1, 2, 2, epsilon 3, 3 diagonal terms summed up together will be its volume change ratio. OK， 好，我曾经跟大家讲过，就是我们之后会有进阶的课程，到时候我们的 epsilon 跟 sigma 都会写成矩阵的形式。当初我们现在这边写的是 gamma gamma gamma， 但到时候就变成 epsilon 1 2 epsilon 1 3 epsilon 2 3。好，它都使用同一个应变的符号。那纯粹要看它的shear 还是 normal， 就看它的下标是不是重复。OK， 那如果是重复呢，就是叫什么？垂直应力 normal strength。垂直应变啊 normal strength。那如果不同的话，它就是 shear strength。那写成这样子以后，当然了，sorry， I forgot to write down. Typically in the normal situation, they are symmetry. Okay, they are symmetry. And also, yeah, that's it. 然后我们就说，我们发现用左边的推导出来，发现 epsilon 1 1 2 2 3 3，也就是它的对角线的就是相加起来，就会是它的体积变化率。好，体积变化率，你这边可以看到这边是1嘛 ，ABC 乘上1，就是它是原本的。那剩下这个就是它的体积变化率乘上它的原本的体积 ABC，就是它增加的变化的率的量啊，哈。乘上 ABC 以后就变成量，那如果不乘上 ABC 就会变成率，对不对哈？比例。Right, that's it. And then we can talk about the strain energy because we have strain on that element, right? So strain energy density due to normal stress in plane stress. And Yeah. So strain energy density. Oh, wow. You see, there's a redundancy here. The so-called strain energy density. Stupid. This is redundancy. Okay. Strain energy is the strain energy per unit and unit volume. I believe you know that. And then the sigma and epsilon curve, when we can have the area under the curve to represent strain energy density, right? So you can imagine that here, this element subjected to sigma x and sigma y, and their change of the length is A epsilon x, B epsilon y, C epsilon z. And then we can know that work done by stress on x surface. The x surface, you see the work done. Work done means the force times the displacement, right? So this is force. Yeah. And this is displacement, right? So when force times displacement and then divide by half, which means that the work, right? And however, this is the wait a minute. Oh, and also the work done by the stress on the y surface, exactly the same, right? Sigma y, sigma x, epsilon y, b a. Okay, so you see, BC is the surface of this, and AC is surface on the top. So you change to the force and then times its displacement. So work done by X and work done by Y, done. So the total energy due to the normal stresses are summed and not together, right? Half ABC times this one. Okay, easy. So the work done by, so it become half ABC and times this sum not together. And then we divide by ABC is their original volume. So it become the strain energy density due to normal stress is half sigma x epsilon x plus sigma y epsilon y, right? Easy. And this is the strain energy density due to the normal stress. Normal stress. We didn't say this is entire total energy density because we have shear, right? So we said shear and the normal, they are independent. Okay, so next one, strain energy density due to the sorry, of the plane stress, which means that we're going to determine the total entire procedure. So this is normal stress and shear stress. Now we're going to include that. So U2, U1 summed up together will be total energy due to the plane stress. All right. So, okay. So the total strain and oh, sorry, I forgot one density. Density. Okay. Total strain energy density. Missing one word. I'm sorry for that. Right. So this is the stress, right? It makes the half pi minus gamma xy is the deformed angle after the deformation. And this is a half pi divided by gamma xy. So the gamma xy is the kind of displacement, right? So tau x is, sorry, it's not displacement. It's a shear strength. So shear strength times the shear stress divided by 12, divided by 2. So you can get the total strain energy density due to the shear stress. And then summing up together, U1, U2, blah, 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 summing up together. Okay. And what I added here is that I just saying that they are independent, right? We just said that before. So independent, normal, and shear, they are independent. Okay, so they can be added. They can be added together. So that's exactly what I do here. And then sum them not together become the sort of ugly form. I can also, there are two forms for the U. The left-hand side is determined by the strength, gamma. And here, the right-hand side, we can use Young's modulus to replace the strength. So I can write down some hint here. Epsilon x equal to 1 over E sigma x minus sigma y, nu sigma y, and epsilon y equal to E sigma y divided by nu sigma x, and gamma xy equal to tau xy divided by G. So if we just substitute epsilon x, epsilon y, and gamma xy, and we can get this ugly form. But yeah, which means that all you need to do is just need to know the stress or the material property, and you can get the strength, energy, density. Okay, that's it. Easy, right? 应该没有问题吧？哦，纯粹只是变数转换而已。Next one, next will be our change to other topic. Okay, now we talk about plane stress. Then we are talking about plane strain. Okay, plane stress, plane stress, plane strain. They are different. Okay, when I was in your age, when I talk about my professor talk about my lecturer talk about plane stress and plane strain, I always confused. I was really confused about this too, and I hope I will put more emphasis on this and try to help you to not confuse as me when I was young. Okay， 就是我小时候看到平面应力跟平面应变，我就都搞不清楚，可能是我没上课没认真听啦哈，所以希望大家可以认真听这一个部分哈。不对了，希望大家都可以听所有的部分。Okay, next one, plane strain. Again, the plane strain means that the strain is only on the xy plane. Okay, no strain in the z-axis. All right, so let's discuss this. Plane strain, 平面应变 plane strain. The stress element deform only on xy plane. So epsilon x, epsilon y, gamma xy. So you see there's a element here, and then only deformation is epsilon x, epsilon y, and gamma xy. That's it. So again, this is our norm. Okay, we know the value. We know the value. So let's see our plane stress in the previous section. In the previous section, we talked about plane stress. The stress means that z direction has zero sigma x, sigma z. Okay, no sigma z. So which means that the differences of the stress in the z direction is nothing. No differences of sigma z. So which means that we can regard that plane stress is a really thin film. How about plane strain? Plane strain in this section is completely opposite. Okay, you see? Let's think about that. Plane strain means that z direction has no strain. No strain. Strain z epsilon z is equal to 0. So which means that their deformation in z direction is tiny. It's tiny, extremely tiny compared to its original length. Okay, so which means that actually plane strength suitable for explaining a sample or the structure with really long axis. So like a wall, like a great wall, 长城. Okay, so you can imagine that if there is a really long, so this surface is just like this, all right, and the components really long at z direction. So this is x, this is y, and this is z. So z actual axis is really long, super long. All right. So even if they have the deformation along the z direction, divide by their original shape, original length, it still become nothing, right? 听得懂吗？平面应变的意思就是说 z 方向没有应变。什么叫没有应变？就是它的改变率几乎为零。那什么意思？就算它在这个长的方向里面有一点点的位移，除上它原本的长度，也会非常的小，对不对？也就是说，那个长度只要够长，你就算有再怎么样一点点应变也没差，因为它根本感觉不出来它的变化。OK，所以平面应变是适合超厚、超长的一个，像例如说水坝 dam， 或是例如说Great Wall 长城这种东西就很适合 plane strip。All right, so this is suitable for describing the problem, the structure or material like dam, wall. Okay, that's it. So let's make a summary on plane stress and plane strain. Plane stress is our previous section. We mentioned in previous section. So you see, sigma z, tau xz, tau yz. So no, whenever the stress component has z, it becomes 0, 0, 0, which means plane stress. But epsilon z have non-zero values because of the Poisson ratio, right? Then we talk about plane strain. Plane strain means that we talk about epsilon y, epsilon x, gamma x. So we have material when their epsilon x, epsilon z, gamma xz, gamma yz, their z component. Whenever their z component appear, they become 0, 0, 0. Okay. However, again, because your epsilon z is 0, this z is 0. Just think about that. You have epsilon x, you have epsilon y. So typically we will affect on z direction, Poisson ratio, right? But there's nothing on epsilon z. So which means that sigma z has something there to cancel the Poisson ratio. So sigma z is non-zero in plane strain. OK， 这边讲一下中文哈，就是说我们说平面应变，它的 z 方向有 z 的那下标的话都为0。好，那我们的 epsilon z 就等于0啊哈，当然了，可是啊你要想想看哦，我们的 epsilon x、epsilon y 都有值这表示说它的 x、y 是有变化的。那既然有变化，那又怎么会 epsilon z 没有普松比的效应呢？那如果今天你这样子假设的话，表示说，如果它即使有普松比，它还是 epsilon z 为0的话，表示说它的 sigma z 其实是有的，然后去把它抵消回来，让它变为0的。OK， 所以这边两边是完全对称的一件事情。OK，plane stress and plane strain, they are different. There's some sort of symmetry. Right. So when we talk about plane strength, now I believe you know that what we are going to do. We are going to do to see the strength component in different angle in the plane with different angle, inclined section, inclined core section, and which called transformation equations for plane strength. We done the transformation equation for plane stress in the previous section, right? Now we're going to do that exactly the same for plane strength. Okay, so under certain loads, we don't, I mean, we don't care. We just say the result under certain load, the object, the material produce epsilon x, epsilon y, gamma xy looks like this. Okay, it looks like that. And then we want to find the inclined section like x1 tilted with theta angle. So we want to observation of coordinates rotated by theta. The strength itself, the strength state doesn't change, right? Just changing the component. But we want to see epsilon x, epsilon y, gamma xy in the x-axis. However, we want to see how about epsilon x1, epsilon y1, gamma x1, y1. Okay, so again, this is known, this is unknown. Okay, then we are going to do the transformation equation. Now, here, we want to see, previously we have this one, right? And we have epsilon x, epsilon y, epsilon x, epsilon x, epsilon y, and gamma xy. So we want to know the shape has the deformation along x1 axis. How big, how great of the deformation along x1, right? So which means that we are going to see a material like this, the stress element like this, and then we want to see its elongation along the x1。就是说啊，我们有一个材料，它是原本是正方形的嘛，哈，是正方形的。不过我们把它拉长到，就是拉长了。那拉长的时候，我们想要去看看，我们原本是说我们那个拉长是拉长 epsilon x、epsilon y、gamma xy，但是呢，我不是要看这个值了，我现在是要看它沿着 x1 的 deformation。我们不是要去看这个咯 xy 跟xy 的轴，我们先要去看 x1 的轴。所以现在我们要做的事情就是要看 x1 轴的 deformation 的位移是多少。So we are going to focus on the deformation along x1 axis under if when epsilon x, epsilon y, gamma xy are the value we given， 就是我们想要知道 x1 的轴的变化量是多少？当我们在 x 轴的地方它是 epsilon x， 当 y 轴的地方它是 y 的 epsilon y 的变化量，然后它的 gamma x y 角度的变化是这个，所以我们必须要去找它们对应关系。So you see, we are going to calculate the epsilon x1, the deformation, the strength along x1 axis. And where is the source? Where is the contribution from to get the epsilon x1 value? Three contribution. Epsilon x will give the contribution to this direction. Epsilon y also will give the contribution along x1, and gamma xy also give a contribution along x1. So we need to add up 3 contributions to get the deformation along x1，这样可以听懂吗 ？x1 的方向被拉伸了，那我们要知道它 x1 方向拉伸多少，可是它是从哪来的啊？当然是从我们知道这3个变化来 ，epsilon x、epsilon y、gamma x1、gamma xy，对，那这3个东西，它 x 虽然往这个方向拉，但是它会有 x1 的分量啊，会让 x1 的方向也变长啊，所以我们要计算出来它这个是多少。y 的话也是计算出来这个多少，伽马也是要计算出来这个多少，所以要3个 contribution 加总起来，就可以知道它们3个之间的关系。Do you see I spent some effort to explain this? Because this is kind of 5% proof that I'm not using force time, stress times area and do the force equilibrium. So this is kind of different, right? So I've spent some time to discuss this. All right, so calculation of epsilon x1. Total elongation along x1 direction has 3 contributions, epsilon x, epsilon y, gamma xy, and we are going to find out what is that. Right, so if there is a stress element like this, and the x1 axis here, and then if this stress element subjected to epsilon x, so the epsilon x times the dx, their original shape, it elongate to this, right? So it becomes this length. So you see, if it becomes this, what kind of contribution will this point this point will go to this point, right? So in this x1 axis, how long will it elongate? You see, this point to this point. In x1 axis, it go a little red arrow, right? So what will be it? What the value of that red arrow? We need to use this triangle. We need to use this triangle, and this is theta, right? This is theta. And you see, what is this one? This length is epsilon x dx, right? Epsilon x dx is a deformation, displacement in the x direction. So this length times cosine theta will be the red arrow. So this is the first one. Oh, sorry, I should mention that epsilon x, epsilon y, and gamma xy are known. They are known, okay? We know the value. So dx is okay. And then this first one is this one, no problem. How about the next one? The gamma, sorry, the y1, y, epsilon y dy. So this stress element under the epsilon y along y direction. So it becomes this. And this one, this point and that point in x1 axis, they have this little tiny red arrow. What is the red arrow value? And we need to use this angle, sorry, triangle. And where is the theta? The theta is this one, right? This one. So epsilon y dy times sine theta will be the red arrow. So this tiny arrow is this one, epsilon y dy sine theta. Finally, in the gamma xy means that if you have a stress element, you subject it to gamma xy, it becomes the dashed line here, and this point become deformed to here. And the component in the x1 axis is this red arrow, and we need to use this this small triangle. But before that, we need to use this triangle to get this one. Okay, and also the theta. Where is the theta? Theta is this theta, right? Theta. And then we are going to get so this is dy, right? And this is gamma xy, right? The green triangle is gamma xy with the open angle times their dy is the pizza shape length. So you can get this one will be gamma xy times dy. So the green pizza shape, the curve here is approximately to the oblique edge of the triangle. 就是这个弧长啊，弧长，这绿色的弧长差不多就是等于这个粉红色的斜边嘛，对不对哈？所以这是 gamma x 乘上 dy，就是这个弧长，弧长再乘上它的 cosine，就会是这个东西。Okay, so this small angle, sorry, small arrow represent this one. So three contribution. You get that? Da-da, da-da, da-da. And then this is delta D. So 3 contribution cos the epsilon x1. Sorry, not yet. Deformation delta D. OK， 才是位移而已啦，还没有到 epsilon x1。所以呢 ，epsilon x1，epsilon x epsilon y gamma xy 造成了 x1 方向的位移就是这么多，有三个 contribution。So elongation along x1 divide by their original shape, original length, ds. Okay, what is ds? ds is a diagonal turn, diagonal length along x1. Okay, in this rectangular. So ds. Delta D need to divide by ds to get the epsilon x1. I believe no problem of that. So ds divide ds. Okay, so everything's here. And what is dx and ds? Dx over dx is cosine, right? And dy over ds is sine. So this is sine. Let me change a bit, change the value. So dx ds cosine, dy ds sine, dy ds sine, right? So become this epsilon x1 equal to epsilon x times this one, epsilon y times this one, gamma xy times this one. So everything is known. Theta is known as well because you are going, this is the problem, right? You want to see specific theta. 好了，听得懂吗？哈，三个贡献都要把它加上去，因为 x 方向的位移，所以造成 x1 也位移了一点点，要找它的贡献。y 位移了，造成 x1 也位移了一点点。gamma x1、gamma xy 转了，也造成 x1 的一点点位移。这三个都要加起来，就是全部的位移。全部的位移再除以它原本的长度 ds， 那正好 ds 跟 dx 跟 ds 跟 dx 跟 dy， 它们都正好有那个叫什么 sin 跟西塔的关系 ，sin 跟 cosine 西塔的关系。Okay, good. So I believe you understand this. Next one is difficult than that. a little bit more difficult. So gamma x1, y1. Gamma x1, y1 is more difficult. I believe it will take time. I cannot finish today, but similar concept, but now it's more difficult. Now, this is x, this is y. Okay, and now you're going to see the x1 and y1, new x1, new y1 axis. So it rotates theta, no problem. And then you want to see gamma x1, y1, which means that you want to see x1 change this angle, y1 change its angle. So this is A, this is B. So A is the deformed x, B is deformed y1. A is deformed x1, B is deformed y1. Okay, so the angle difference between A and x1 we call alpha. The angle difference between B and y1 is beta. Okay, so gamma x1, y1 equal to alpha plus beta. Okay, so we need to calculate alpha and we need to calculate beta. And summing up together, it becomes gamma x1, y1. Okay, so now it will be a little bit difficult. We need to firstly determine alpha. And then we determine beta. And then summing up together become gamma x1, y1. Let's take it step by step. All right. You see, alpha is kind of counterclockwise. Counterclockwise. Okay, and beta is clockwise. Clockwise. Okay, so they are kind of different, but it's okay. Let's continue. So we focus on alpha first. All right. So again, you have exactly similar, exactly the same element, and this is ds, original oblique diagonal length, diagonal lines, and then you change the epsilon x. We still need to get the three contribution, right? So epsilon x dx, it makes this rectangular longer, become the dotted shape. So this ds become this dashed line. So which means that the angle change in x1 is this small arrow. Okay, the small arrow. And how can we get that? We can get that by using this triangle, right? And theta is this one. Okay, this is theta. So how can we get that? We need to get this piece length, or well, 弧长, the arc, the length of the arc, and then divide by its theta. Oh, sorry, divide by the ds, and then we can get the red small angle. Okay, so we call this alpha 1. Okay, alpha 1. Alpha 1 equal to the epsilon x dx sine theta, right? You can use this epsilon dx, and we want to get that one, so times sine theta, we can get this one. Okay, epsilon x dx sine theta divide by ds, we can get alpha 1. Okay, so this is a little bit difficult now. epsilon x dx sine theta is this one. And divide by ds, it becomes alpha 1. However, did you notice that alpha 1 is clockwise? So this is counterclockwise. So this is negative. Okay, so this is the first component. Right, I will continue the rest of the component in the next week. Okay, so thank you. See you next week. If you have any questions, just come here. Bye-bye.谢谢。这样也不能抄了。好，就这样。